This last part of the lecture is going to be about inverse problems and how to use reduced order modeling to solve them numerically. And in particular, I'm going to present results on optimal state and parameter estimation algorithms. The agenda for this last talk is going to be as follows. In fact, I'm going to present what I'm going to understand by a state estimation problem. It's a particular type of inverse problem. For this type of inverse problem, we are going to define a benchmark of what is the best one can do to solve it. And we are going to see that, in fact, the best that we can do, the best performance we can get, is very difficult to achieve with a numerical physical algorithm. But the good news comes in the second part of the lecture, in the sense that we can develop algorithms that provide near optimal performance and that are implementable and that are based on piecewise affine algorithms in the way I'm going to describe later on. But this is going to be based on piecewise affine approximations as the one that was in the blackboard, in which I was showing a V-shaped manifold, and then we were doing a splitting of the manifold and two linear approximations. Finally, depending on how much time I have, I would like to show you some applications and some current developments that we are doing in my group. The first one that will be taken as an illustration for the whole talk will be on biomedical problems. But if time permits, I would like to show you some recent results we are developing with Agustin Somacal on shape recovery, on Hamiltonian problems with Federico Vismara, conservation laws and Wasserstein gradient flows with Pratik Rai in the audience, and also Wasserstein PD GCNNs with Dan Bond, my PhD, who is also in the audience. If by any chance there's no time for me to show a glimpse of what they are doing, please go talk to them because they will be glad to exchange ideas with you and to show you about their field of research. So let's now go for the first part of the lecture, optimal benchmarks for state estimation. What happens? This first part of the lecture is going to be to present results that I have mainly developed with the three people over there, Albert Cohen, Wolfgang Dahmen, and James Nichols. And the illustrations on biomedical problems have been produced with Felipe Galarce, my old PhD student, co-supervised with Jean-Fred Gerbeau and Damiano Lombardi from INRIA. So, what is an inverse problem? In an inverse problem, we want to find the cause of an effect that we are going to observe only partially. As a first example, consider the problem of reconstructing a pollution field in a city. This is the map of Paris, the inner city of Paris. It is about 10 times 10 kilometers square. And in this area, in fact, we have about 15 sensor locations, which are these little dots over here. On these little dots, we are collecting every hour, more or less, the amount of pollutant concentration that we are finding at this point. And what people are doing in several institutions is to gather this data and then produce an estimate of what the pollution is going to look like at every point in the field in time, and also maybe to forecast what is going to be the level of the pollution at every point. So you can see that, I mean, this is an extremely ambitious task because it's a very large domain. I only get 15 data. From this 15 data, I want to produce something which is very high dimensional. It's a spatial field in a large domain. In order to have any hope to say something about my reconstruction quality, I need to add a prior assumption that my field somehow has a certain shape expressed in a way that can help to say anything about the predictive capability of my algorithm. The classical priors that are used in inverse problems, we can categorize them essentially into two main families. The first prior is to make a prior assumption on the regularity or the sparsity of the field that you want to reconstruct, to assume that, for example, you have a field that is CK regular or something like that. This type of prior assumptions have been used a lot, for example, for inverse imaging problems, in which the observations come from images. Instead of data from sensor location, we can imagine that an image with a certain resolution is also an observation of something I want to understand. For this, regularity and sparsity have been very common priors. We are not going to take this route in the approach I'm going to present. The prior information we are going to assume is that the physical phenomenon we want to understand is driven by a certain PDE model. May it be here, for example, the Navier-Stokes equation, so diffusion equation or something like this. And in addition to this, there are here two families of approaches that one can take down this path, which is the so-called Bayesian approach to solve the inverse problem. And in this talk, in fact, we are going to see what can be understood as a deterministic counterpart of the Bayesian approach. And I'm going to comment on the two, on the difference between them. But just so that you keep in mind that that's kind of the flavor of what we are doing, connected to the whole landscape of inverse problems that you could encounter. So the mathematical setting in which we are going to work is the following. V is going to be our ambient Hilbert space. It is going to be posed over a spatial domain omega of Rd. In this example, omega is the times 10 square. And V can be, say, L2 of omega, H1 of omega, reproducing kernel Hilbert space. The catch is that this space is going to be potentially very high or infinite dimension. And so we are going to assume that the PDE model that we have at hand, so it is a parametrized PDE. It is going to be driven by this operator equation that you have seen before, with certain parameters, theta 1 to theta p, that we are going to assume they belong to a certain compact set theta here. This defines the solution manifold as we said before. So now, what is an inverse problem? First, let us agree on what is a forward problem here. The forward problem here is that you give me thetas and I compute u of theta. To do this, you can use any solver you wish. You can throw your favorite finite element solver, finite volume solver. You can use also the reduced modeling techniques that I have discussed in the previous lecture. But the upshot here is that this is for us a forward problem, the parameter to solution map. In the inverse problem, u is going to be unknown. And theta is also going to be unknown. Instead of giving theta, we are going to give m linear measurements, m real values, z1, z2, zm. These zi's, they are going to be generated by the application of a linear function li applied to u. These li's, they belong to the dual of my Hilbert space. And because I am in this Hilbert space, they admit Riesz representers that I denote by omega I. So by the Riesz representation theorem, these observations li of u, they can also alternatively be written as the scalar product of some elements omega I from my space V against my unknown u. So in practice, I don't have u, and I am going to assume a shape for the omega i's. Just let me explain this in the next slide. I am never going to do this operation myself, in the sense that I am always going to be given the outcome of this operation through the real values zi, okay? And so in the inverse problem, what we want is to invert the cascade of forward mappings that take me from the parameter to the solution, and from the solution, by application of the LIs of u, I get the observations. So in the inverse problem, I want to go from the observations back to the state u. This is going to be the problem of state estimation. And from the observation z, directly back to the parameters. This is a parameter estimation problem. So maybe one thing that is nice to remark here. So when I go from my solution to the observations, I apply a linear mapping. It's a linear mapping to go from here to here. Therefore, the inverse of it, for state estimation, is also a linear map. So one may think it's then an easy problem. But the thing is that this guy here is defined in an infinite dimensional space. So the dimensionality is infinite. And the dimensionality is the reason why state estimation is a hard problem. When I go from observations back to parameters, so maybe I may not have a lot of parameters to infer. Sometimes I do, sometimes I don't. But what is really hard here is that the mapping from the observations back to the parameters is very nonlinear. Okay? So in the following, we are rather going to focus on the state estimation from the data to the state, but I will say a few words also on parameter estimation. Let me just clarify what are these linear functionals, because it may be confusing. I have the impression on a first contact. The LIs that I have introduced, they model the response of a sensor. They are kind of fixed by the nature of the problem and the nature of the sensor. They are known to us, okay? So this is something that we know. Some examples. If I take a reproducing kernel Hilbert space, an example of Li of u could be that I choose Li as a Dirac delta centered at some point, xi. And therefore, its application is just getting the information of my state u at a certain point, xi. This is what happens, for example, in this application about pollution. If I assume that my field is regular enough so that I can assume that my solution is continuous and approximable in an RKHS, this can be seen as a point evaluation, and therefore the Li here can be seen as a Dirac delta, as is in this way over here. Okay? Because I choose to work in a reproducing kernel Hilbert space, then I have to know what is the Riesz representer of my Dirac delta in this space to figure out what is the Riesz representer omega I. Okay? And so in a reproducing kernel Hilbert space, this is going to be related to the kernel function that I am going to use for my problem. Another simple example is if I work in L2 of omega, I can think that instead of having my measurements here modeled by a pointwise evaluation, I can think that I am given a local average around my point xi. To model this, we can take this type of integral of u of x in which we integrate it against an exponential kernel function centered at xi. So this function vanishes very quickly far away from xi, and it's a local average around xi. So this kind of thing can be the action Li of u, and in this case, in the L2 norm, the Riesz representer is just going to be given by the exponential function itself over here. Okay, and so an example in which we may want to work with this kind of Li's of u comes from biomedical problems over here. We have applied the methodology I'm going to show you to the problem of state estimation in the carotid artery. It's the artery that runs here, more or less. And data that we can get from the carotid artery come from Doppler velocity measurements. And they look this way. It's a map in which we have a pixel resolution. On each pixel, we are looking at the velocity of the blood flow going through the pixel. It's a 3D quantity, but this velocity vector is kind of projected into a certain observation plane. And this is what we get as an information, a 2D projection of the velocity into a certain plane. And the task can be given this kind of observation of the velocity, use all our methods, and assuming that, for example, here the flow could be modeled possibly with a Navier-Stokes equation, combine this observation with the knowledge of a Navier-Stokes equation in order to reconstruct the 3D velocity in the whole 3D domain, and maybe even more ambitiously to try to reconstruct what happens beyond the part that we can observe. And this is relevant for biomedical applications because sometimes we cannot receive images from anatomical parts of the artery. And in order to make sure that there's no stenosis and things like that, one can resort to the techniques I am going to show you. So this is a slide again saying that we will focus in fact on state estimation. And now let us define the task that we want to do. In the rest of the talk, in fact, I am going to assume that my observations don't have any noise and that my PDE model is perfect. This is absolutely an idealized situation. It's completely far-fetched. And I will comment on this at the end of the talk to show you how to account for these errors in what I'm going to say. So, but for simplicity, let's assume this. So now, from the unknown U that we want to reconstruct, this U, we are assuming that it is in the solution manifold of my PDE. There's a parameter that realizes the true U I would like to reconstruct. But since I don't know the parameter and instead I'm given the observations, I need to do something clever to come up with an approximation of my U. So I'm giving my observations. The first thing I'm going to do is to take the Riesz representatives of my sensors. I am going to assemble them and consider the linear span that they generate. This space is W, and I'm going to call it the observation space. It's going to somehow represent what I can see with my sensors. And it turns out that we have the equivalence that knowing the values of the LIs of U is in fact equivalent to be given the projection of the unknown U onto the space W. And so this is going to be an element of my space that I am given thanks to the observations. Now our task is going to find a reconstruction algorithm A that goes from my observation space W to the full ambient space V, such that whenever I'm given the observation data, A of the observation has to approximate the state U the best I can. And just here, to connect with previous discussions, observe that A is a decoder. It is going from a space of dimension M, the number of measurements, to an ambient infinite dimensional Hilbert space. This can be understood as a decoder. I want to build a particular decoder with a particular nature of my input. And also to visualize what is going on in all this, maybe the picture to keep in mind is the following. So my ambient space is my V over here. My observation space is going to be represented by this W. And I know that I have a manifold set of solutions M, and my unknown function U is going to lie in this manifold, but I don't know anything about it, except that when I project it to my W here, I am getting this point, PWU, okay? So what I know about this problem is this one, and somehow what I want to do with my algorithm A from W to V is to start from here and start exploring the elements in this perpendicular fiber and somehow come up with something that approximates this U. So you can see that this is a super hard problem. There's an infinite amount of solutions to it, but if I already restrict myself to saying it's the element of this fiber intersected with the elements of the manifold, then I am already starting to diminish the amount of uncertainty that I have in the inverse problem that I want to solve. So that's the situation, and this is the element I would like to approximate. So we need to agree now on what is the quality of a reconstruction algorithm. So you give me a decoder, an algorithm A, and I want to know how good this is. Again, I am going to define it similarly as for previous discussions. I take my algorithm A, I look at I apply my A for the given data PWU. I look at the distance, the error of approximation to the given U for all the elements of the manifold. And this is going to tell me how good I am in doing the reconstruction when the true states U, when they range in the whole manifold, this is the worst case approximation error. Now I am interested in the algorithm that performs at best. Among all possible mappings, the one that performs at best is the one that minimizes this error, right? And so I'm interested in characterizing the algorithm that realizes this minimum, if there is one, and in seeing how I could compute it possibly. And so the remarkable thing that happens, that has been proven, is that as soon as M here is compact, in fact, there is a minimizer. It's not an inf here, it's a real min. And one can characterize at least one algorithm here that reaches this minimum. Okay, and it has a very intuitive characterization, which I'm trying to convey through this example. Here, the observation space W, it's the same game. This is W. I am getting here an observation omega over here. So I know that all the possible states of my system, that they are going to lie in this fiber here of dark blue color that I'm calling here M omega. Okay, this is the same slice I have drawn here. With the data that I have and the manifold that I have, in fact, I don't know anything else about where my true U is going to lie. It could be anywhere in the fiber, anywhere in the line. Any U here could be happening, and I don't know which one. Nevertheless, I need to make a decision to output something with my algorithm. And it turns out that the best choice I can make is to output the center of what is this segment over here, this fiber over here. This is the element I would ideally like to output, and we can prove that this is the choice that is going to give you the best reconstruction error. Okay, so technically speaking, in general, I mean, this thing is in infinite dimension. This is not really a segment. It has a complicated shape. And what I call this as a center, it's what is called the center of the Chebyshev ball of M omega. What is this? It's kind of very simple. If this is M omega, I mean, M omega, we have to imagine that it's a kind of a very crazy set, in fact. Okay? This set, I can try to contain this set in a ball. And the ball of smallest radius that I can use for this, its radius, this ball of smallest radius has a center. This center is this one over here. And this center, I mean, I also get a radius of the ball. And the radius of the ball is connected to the approximation error that I am going to have when, for example, if this is the true U that is arising, that is really taking place, the error between this U and my approximation is going to be equal to the radius of this ball. Okay. Any questions so far? No? Yeah.
I didn't understand why, when we are given a measurement W, we know all the fiber M of W.
No, we don't. That's the drama of it. I mean,
okay.
At the analytical level, you can characterize this set as the intersection of the elements of your manifold that project into the W. This M of omega, this fiber is well defined in a sense, but characterizing it in practice, it's a no-go. So I cannot characterize it, and therefore I cannot even also, in addition, go and compute the center of the Chebyshev radius of the thing. It's unfeasible. This is why we need to kind of go for suboptimal reconstructions, for which we are going to try to claim that they are near optimal, that in a certain sense they will do almost as good as what I'm showing to you. Yeah. Yeah.
So here the optimal point was the center because you were using the worst case error.
Yeah.
But if you would use like an average error, it wouldn't be the center, right?
Thank you for the remark. I had forgotten to comment on this. Indeed, another measure of quality could be to replace this max by an integral, by an average. This assumes that the elements of the manifold have a certain probability distribution. And in fact, when I do this replacement, I fall into the ballpark of Bayesian inversion. Bayesian inversion, in fact, is interested in the quality, in the average reconstruction quality. And when I go down this path, I kind of I'm losing the description that I am giving. One can say certain things. I can tell you later on what is known about the optimality of this. But surprisingly, changing this into an average is going to turn this kind of analysis a bit more difficult. And this is surprising because the max over here, it's in principle, it's a non-differentiable function. So yeah, one can think, it's difficult. So to some extent it is, but not on all aspects. It's kind of surprising.
Okay, no other questions.
Okay, so as we were just commenting on, this thing is completely idealized. I cannot realize this in practice. So what to do? Now, this is the second part of the talk. We can actually build a near optimal reconstruction map that is feasible. And for this, I am going to first define what is a linear reconstruction algorithm. And then I will define what is a piecewise linear reconstruction algorithm and why I can claim that this can be near optimal. So what is a linear reconstruction algorithm here? Now, it means that I'm going to land in the mapping A from W to V. In fact, I'm saying that I land on a space from V which is finite dimensional. And for this, what I'm going to say is, suppose I have fixed an affine subspace, or just for simplicity, suppose that we work with a linear space Vn over here. The dimension of Vn has to be smaller than m, the number of data observations that I have. Then I claim that, in fact, the reconstruction mapping that takes any observation W and returns me an AW, which is defined in this following sense that I'm going to make a drawing on the board. This thing is, in fact, a linear or an affine algorithm. I land in V here, but I land in a linear space involving my Vn. And this thing, the performance of this algorithm can be very nicely bounded by quantities that are very intuitive. But so in order to explain all this, let me again try to make a picture of what is going on. I have my W, my manifold. Suppose I have selected a linear space over here. Okay, it's a very unfortunate choice. Suppose this is my Vn. This is my observation. So what is this algorithm telling me to do? I have to move in the fiber omega plus W perp. This is this fiber over here, omega plus W perp. And I am going to examine the elements in this fiber and look for the ones that are at closest distance to my Vn. So I go along this fiber, I look at the distance to the element Vn, and I have to pick the element that is at a smallest distance. Here in my picture, they are intersecting over here, but in general, they are going to be disjoint. The error needs not to be equal to 0. This is going to be my A of W with the algorithm that I am suggesting to work. And so this output A of W is in fact going to live in this linear space, Vn plus something involving W, which yeah, basically we don't care, but so this is a linear space. And so this is why this is a linear approximation, because in the end I land in the linear space. So the performance of this thing can be bounded as follows. So it is bounded by the product of something that we hope is good, epsilon n. What is epsilon n? It is the quality of approximation of my elements in the manifold with Vn. So I look again at the element of my manifold that approximates at worst to Vn, and this is going to be epsilon n. So we have seen that for elliptic problems, working with a linear space is very good, and this epsilon n can be very small for n that doesn't need to be very large. Okay, so that's epsilon n. Hopefully, for some problems, is a good thing, and we have here a stability parameter 1 over beta. This beta can be interpreted as the cosine between the angle of the two spaces, the observation space Wm and the reduced space Vn. So it's the cosine of these two angles over here. It means that when the two spaces become orthogonal, the cosine is going to tend to 0. So I'm going to swallow here a very large constant, 1 over 0 basically, something very large. Becomes very unstable. That is bad. But when they start to be more and more aligned, this cosine is going to go to 1, and it's going to be a very favorable situation. Okay? So there's going to be a trade-off between the quality of approximation of Vn and the stability between my Vn and my W. there's this kind of tension. And if we assume that the sensors are placed by some colleagues from applications, and if I cannot touch at my W, I can start thinking about, okay, so what is the best space Vn that I could use for my task here? And one can characterize this optimal space. We did this in a paper. Roughly speaking, it is somehow similar to thinking that I have to optimize the effect of both these terms in a clever way. It's very computationally complicated to implement. It turns out that there are spaces, linear spaces Vn, that are suboptimal for the task, but that work very well. They come from reduced order modeling, and we have been discussing them in the previous lecture. They are suboptimal because they really try to optimize over only the error epsilon n. And so here we have the tension between the accuracy of approximation epsilon n and the stability 1 over beta, and sometimes they may be fighting against each other. So this thing is not really optimal, but for all practical purposes, it often works very well. One can ask, of course, the complementary question, which is, if now I fix my Vn, what is the best placement of my sensors that is going to give me also the best reconstruction? One can also ask oneself this kind of questions, but I am not going to show results on this. Let me show you how this works in a concrete example. In the work with the biomedical applications and the carotid artery, for example, our goal was to reconstruct this kind of velocity fields and also pressure fields out of this 2D velocity projections. What we get in the end from the data, I mean, these were kind of the true fields we wanted to reconstruct. And from the observations we were being given, we were able to reconstruct very nicely the whole artery. But I'm realizing this is maybe not the best example. I have this other example over here is probably better. What we are seeing here is a classical benchmark example in fluid dynamics. It's a flow past a cylinder. There's a flow coming from the left to the right. There's an obstacle over here. And we have an underlying Navier-Stokes equation driving the dynamics of this flow. We assume that there are parameters underlying these Navier-Stokes equations, like Reinholds number or viscosity and this kind of stuff. For a given configuration, we are going to have a certain evolution. We are not given the parameters, but we assume that we are given pixelized information of the beginning of the flow. And our goal is from this information and a reduced model for the Navier-Stokes equations, reconstruct with the algorithm that I have just explained over here, reconstruct what we are going to get. So what we get is here on the third line. As you see that, I mean, we get a very good reconstruction. And as we make time evolve, the things are working very nicely. And this has been produced with a reduced model of dimension, which is relatively small, but I don't really remember, maybe a dimension 15 or something like that. So it's really in a very reduced, at a very reduced cost, so to speak. So what can we do now to use this? Okay, and this algorithm is in fact very friendly, because when one really starts examining it, one realizes that there's an underlying discrete least squares problem, which is very easy to invert. And therefore, computing this reconstruction can be done very easily and at a reduced cost, involving the number of degrees of freedom here, little n. So one wants to use this algorithm in order to kind of build up more complicated reconstructions, because this one is so easy to compute. And so we are going to show you how to compute it in the hands-on session. So the first thing we may try to do is to go piecewise affine. By this, I mean that we are going to think again about the example of a V-shaped manifold of solutions. And what we want essentially is to find a procedure in which we are going to make a separation of the manifold into, for example, two pieces, the red piece and the blue piece. And for each one of them, we are going to build a reduced space V1, one being, a reduced space for the first part of the manifold, and another reduced space V2 for the second part of the manifold. Now what happens is that if we agree on a procedure to do the splitting of the manifold, then what is going to happen is that if I get this observation W, it may have been generated by a true U that is over here. So I can run my reconstruction algorithm with this observation and this first space, but then I can also do the reconstruction with this observation and the other space. And since I don't know my parameter, nobody can really tell me which is the reconstruction that I have to choose, whether the first one or the second one. It is fairly obvious in this example that there's one that I definitely wanna use. It's going to give me an output that is going to be over here. The other one would give me an output that is going down here. It's super bad. So in order to, there needs to be a way to really take a decision here. And the way we took the decision was in fact involving kind of a complicated operation, in the sense that once we had a candidate reconstruction, this one or the other one, we somehow wanted to compute the distance of our solution to the manifold. And the one that is the closest one is going to be our selected reconstruction. So I'm running out of time. I cannot show you the full development, but I would just like to say here that we have a procedure which can be computationally intensive, and I can give you details later on in the break for those who want. We can make a selection there, and with this selection, we are going to get a piecewise algorithm, a piecewise affine algorithm. And there's the following remarkable result that we developed a couple of years ago. Now, I fix myself a given target tolerance sigma that I want for my approximation. It turns out that I can find a partition of my manifold in pieces like this. I can start decomposing more and more my manifold. We can find a partition of the manifold such that when we take this partition, we do the reconstruction with the selection that I did not have time to show you, then the performance of this algorithm here, it is not going to be, it is not going to beat the optimal performance of the optimal algorithm with the center of the Chebyshev ball, but it is going to be bounded by the optimal performance of the algorithm that approximates not the original manifold, but a manifold that has been thickened by a layer sigma, that has been thickened by a layer sigma. And what I mean by this is that I take my manifold, I take my target accuracy sigma, I imagine that I start rolling a ball of radius sigma around the boundary of my manifold. This is going to give me a thickened manifold M of sigma. Okay? So if I fix myself a radius sigma there, I can always find a partition of M for which the performance of my algorithm is going to be better than the performance of the best algorithm of M of sigma. And we can see that when sigma is not very large, in fact, both performances over here, they are not going to be so far apart. This proves that if we know how to refine this thing, and we know how to do the selection correctly of between the reconstructions with V1 and V2 over here, we can get a near optimal algorithm for reconstructing. What happens as well is that in the end, this sigma over here can also account for noise and model error in the analysis. I can imagine that instead of my function belonging to the manifold M, it may well be that I have an error in my PDE model, and that I belong rather to an M of sigma. Somehow it means that there is going to be an incompressible sigma that I cannot go below, that is going to prevent me to make this sigma go to 0 due to noise or model error. Okay? The quantification of this sigma for noise and model error, it's very, it's kind of difficult. This is one thing that I don't like about the result, in the sense that it doesn't really give a critical mechanism to discover whether your reconstruction, if we know that we lie in the manifold or close to it, we have the best method that we can ever dream of. The problem is how to make sure that we really belong to the manifold. What is the error there? The method is not super critical with this. This concludes this part of the talk. I would like to show you some current developments that we are doing these days based on the whole methodology I have shown to you. The results so far that I have discussed, they involve piecewise linear spaces. One can think about using nonlinear spaces in order maybe to use less partitions in this kind of approach over here. Sometimes, depending on the problem, I may need a lot of partitions, in fact, to have a good result. So can I use nonlinear sets in order to kind of do things that are a bit better? And also, maybe, can I address more exotic problems with this? So the first example is this shape reconstruction with a nonlinear Vn that Agustin Somacal is developing in his PhD thesis with Albert Cohen and myself. And Mathieu Dolbeau, another PhD student, was also a bit involved in the thing. The main idea, the main goal that we are trying to pursue here is the following. We have a certain shape, this Darth Vader, for example, and the game is that our observations Li of u, they are going to be cell averages. Here, I don't know if you see in the screen, there's a grid. In each part of the grid, we are assuming that we don't observe the shape. Instead, we are given just the local averages of the shape inside each cell. And the goal is that we want to reconstruct from these cell averages the shape of the underlying, the border of the underlying shape. So in order to do this, what we are going to use as a reconstruction set, Vn, it is going to be functions like this. So if I have one grid cell, I am going to try to do the reconstruction with families of functions that are, for example, piecewise affine. And then I can parameterize this by changing the slope and the position of the slope. And this is going to generate a family of functions which is actually nonlinear, and which we can try to optimize in a certain way. And eventually we can do a reconstruction that looks like this. We can, beyond working with only lines, we can work with higher order polynomials, for example, parabolas. And we can get a better approximation. Here we are using parabolas, and we see that the approximation improves. So this is a very funny example that we have produced. Another work that we are developing at the moment is with Federico Vismara and Cecilia Pagliantini. We are taking their methods on dynamical low-rank reduced modeling in order to solve inverse problems on Hamiltonian systems. The bottom line here is that in their work, if you remember, now I am going to have an m of t and a Vn of t, that Vn is going to evolve in time, and the measurements here, W, are going to evolve in time. So the question is, okay, so we can for every time step, we can do the reconstruction more or less in the fashion that I have shown to you. But what happens is that the solutions, they have a localized support. And I need to move the sensors in order to hope that I can do a decent reconstruction. Where is my... here. So this is a time-dependent reconstruction of a 2D Schrödinger problem. The points that you're seeing are the location of the sensors. We are moving them because if we don't, what happens is that the solution has a localized support. Over here it is moving. And if I place my sensors cleverly, maybe in the original location of the bump is going to move, and then I'm going to get at a certain time observations that are going to be all equal to 0. So in fact, this is an extremely unstable problem. I am not going to be able to reconstruct anything. To have any hope, in fact, I really need to move my sensors along the way, and we are developing methods to do that. And it's a kind of a pretty funny project. The last two works I would like to put forward is the work we are doing with Pratik Rai, who is here. It is about sort of doing the same ideas that I have explained over here, or doing the same ideas of moving the sensors for Hamiltonian problems. But now we want to redefine everything in the Wasserstein space in order to address conservation laws and Wasserstein gradient flows. So this is a work that we are currently doing. We don't have extremely consolidated results, but only first attempts in which we take, for example, a solution of a KDV problem. We assume that we place the sensors in these blue dots, and we see that instead of using reconstructions with linear combinations, if I use my Wasserstein barycenters, there is hope to really reconstruct very accurately the solutions also with this kind of method. And finally, something a bit tangential, but also connected with inverse problems, is the work that we are doing with Dan Bon in his PhD. Dan is also here in the audience. This is a work done with a colleague from TU Eindhoven, Remco Dodds, who is an expert in applied differential geometry. I'm not sure if he was the one introducing PDE GCNNs. Was he the one? Okay, so he introduced a very interesting analogy between convolutional neural networks, the basic operations that are inside a neural network, and operations that, and the basic operations can be understood as solving certain PDEs. The idea is the following. In a traditional convolutional neural network, the classical operations are the convolution, but now we also have a pooling operation in which basically we are kind of stretching or contracting the support of the solution, and then we have the application of ReLU nonlinearity. So Remco and his collaborators, they have kind of observed that these kind of layers over here, they look very analogous to a certain PDE evolution, in which, in fact, the PDE involves convection effects, diffusion effects. The dilation effects of the pooling are going to be expressed by Hamilton-Jacobi equations, and the erosion parts as well, but with a negative sign over here to do erosion. So the whole traditional convolutional neural network layer can be understood as the PDE evolution involving all these parameters. So it's a PDE of this type. We are solving the PDE not completely in one go for all the terms, but in one of the layers we solve a convection, in the next layer we solve a diffusion, in the next layer we solve a dilation, and so on. And so the parameters involved in this PDE can be connected to the parameters that we use to do the pooling and everything else. And now the fun fact is that this thing seems to work very well, for example, for imaging problems, in which Remco is working very much. And now, of course, conceptually one can ask, okay, now I want to redefine everything. Instead of for input functions, I want to redefine everything for input measures. And therefore, these PDEs, they are now going to be recasted as PDEs on measures and involving gradient flows and a bunch of stuff. And these equations, they are also going to involve parameters, which we are going to train and see how they behave. So we are applying, so we are kind of enlarging this setup to now Wasserstein PDE GCNNs. And for the moment, the example of application that we have is the following one. The task is to recognize this kind of lines over here. And what we get as an input is that the line has been kind of erased and there is a noise in the image. We get this kind of inputs, and the task is to learn to go from this noisy image to this type of reconstruction. And so far what we get with the current code that we have for Wasserstein PDE GCNNs is that the output that we get, it's here in the third line. So we see that we very clearly kind of distinguish where the line is. What doesn't make us very happy is that these lines are a bit thick, and so we are thinking how to kind of improve all this. This leads me to the main conclusions of this part. We've seen in this talk the theoretical foundations for optimal algorithms for state estimation. Reduced models are crucial to develop viable algorithms. There's still plenty of room to do nonlinear approaches, in fact. As somebody pointed out, what we are kind of, the main distinguishing feature between what I have just presented and Bayesian inversion is that we look at the errors in the worst case sense. And this leads to kind of more deterministic notions of benchmarking and accuracy quantification. And I've shown to you works on these Hamiltonian systems, conservation laws, and Wasserstein gradient flows. And we can even start addressing imaging problems by this analogy of convolutional neural networks with PDEs and the extension to metric spaces. Thank you for your attention.
So this ends Olga's lecture. Thank you so much. So please, questions?
Hello, thank you for the talk. So I was wondering, have you considered cases when that you could have the same U generated by two different parameters?
Yes, this is an excellent question. Somehow, okay, there's two layers of answer to you. The first quick answer is no, we did not consider it. We are always rather thinking of a situation in which one parameter theta, there's here now some sort of background space theta that is going to generate me U of thetas here. And in general, we are going to assume that the mapping is 1-to-1. But what happens is that somehow to derive this reasoning about these reconstructions, we sort of forget about this. We are only now looking at the manifold. And so even if there were two different thetas that generated me the same U of theta, at this level, I kind of don't care. Because I only want to approximate the U and not the theta. Right? So from this, in this respect, somehow we don't need anything to know about this. But if we then need to do a parameter estimation, we are in trouble if this is not well defined. And for the strategy that I develop over here with several options, in fact, there is going to be underlying a certain parameter estimation problem. And there, if you have the problem that you are raising, you're in trouble.
I see.
Yeah.
Well, thank you. Oh, just one thing. And what about parameters that are measures?
Sorry?
Parameters, like the space of overlying space of parameters is a space of measures.
What happens if the space of parameters is also generated by measures?
Oh, like for example, theta is like could be like Dirac at a family of points, or I don't know, some general measure on Rn.
So here we are often thinking that this is in RP somehow.
Oh, okay. I see.
But we can consider more exotic things. I have never thought about thinking that this is an element of the space of measures. I don't know what would happen.
Well, thank you.
Yeah.
Other questions?
I would like to know how the algorithm behaves with respect to the number of measurements.
With
Because-
okay.
Because, for example, for the 2D Schrödinger example, you have very few measurements, and so is it a constraint? Because you could also have sensors all over the grid so that you know that the bump will be covered wherever it is.
Yes. Several answers again. One needs to decide what we agree the sensors can do or cannot do. Moving them is actually debatable because maybe I'm not allowed to do so. If I allow myself to place them on a uniform grid, yeah, then of course I am going to cover the whole space and probably everything is going to be fine. We were developing the algorithm in the spirit of thinking, okay, we don't have a lot of observations, still we want to say something.
But is there like a numerical constraint to not have too many measurements?
No. You can take m to infinity. You can fix a reduced model Vn here for a fixed n. You can ask yourself what happens when I start increasing the amount m of measurements. What is going to happen eventually is that your reconstruction is going to give you the exact solution as m goes to infinity. So somehow there's a sanity check over there, which is telling you all things are going to be fine somehow.
Okay, thank you.
Any other questions?
About the sensors, in the last video you showed, how do you instruct the sensors to follow the solution?
Yeah, I didn't have time to show you this. What we are leveraging is this stability parameter I have introduced, the 1 over beta. Where can we see this? Here, I am going to start making reconstructions for my m of t, in fact, now, okay? And like when we didn't have the time dependence, I can again bound my approximation with this epsilon times 1 over beta, okay? And so the 1 over beta, when it goes to 0, it's an indication that your reconstruction is going to be very, very bad, very unstable from the measures, from the observations that you're getting. It's an indication that you should reconsider repositioning your measurements somewhere else. So we are sort of following a strategy in which we are trying to make beta at every time step as large as possible. Okay, so this in fact leads to a beautiful development because there are going to be some Euler-Lagrange equations involved that one has to solve for the location of the sensors. It's kind of beautiful, but the idea is I want to maximize my beta at every time step.
Okay, thank you.
Yeah.
And in last question, in slide 22, yeah, the error corresponding to M and the error corresponding to the enlarged manifold M sigma,
Yes.
are they usually far or are they what is the gap between the two of them?
Yeah, we can see this in the drawing, probably very good. Suppose this is my M of sigma. Okay. The approximation error of this lies over here, fix this lies. The approximation error in M is going to be, I take the center it is going to be of this order, right? The approximation error of the thickened m of sigma is roughly going to be of the order of the radius plus sigma, roughly. So if sigma is not very large, we are not really changing very much. Does this make sense?
Thank you.
Yeah, yeah.
Okay, so I would suggest that we continue discussions at the coffee break, and there is a computer session at 14:30, so please be back.